Hi everyone, glad to be here on DevOps. We are going to talk about some performance today, only a tiny bit of it. We'll see some throughput effects and what actually, where to pay your attention. And it's also about Java. I'm proud to be a part of this great open source project called OpenJDK. I'm an OpenJDK committer, and the company contributes eagerly to OpenJDK and different other open source projects like Linux. We release multiple products based on that open source. Our own distribution of OpenJDK called Liberica JDK, which is the default JDK for Spring Boot containers. And also we have Liberica Native Image Kit, which is a build of GraalVM Community Edition, and Alpakita Linux, which is Alpine-like system. I'll mention it a bit, but that's not today's topic. So let's start with a story. We work for fun because we love programming, right? That's the thing that we would do for free, but we actually earn money doing that. And that money comes from some business, right? We write some useful programs that help people to do stuff. And that systems I used, or that solutions I used to earn some money, well, we create them, but nowadays, all the digital part of the world, it experienced great transformations. For example, a good friend of mine from a very large company in the United States described that they moved their production to a new paradigms. Like they started to use microservices to write them. They wrote a lot of microservices, made such a great migration from that monolith solution to a microservice-based one. At the same time, they migrated from their own data centers to a public cloud. So that was a great successful project. Well, what could go wrong here, right? In that project, they created teams successfully developing that microservices, developing their code. They created DevOps teams, or just selected some DevOps or grew some DevOps people that helped to prepare and deploy that microservices. They had platform teams and cloud operations who managed and cared about stability and deployment in real production. Well, all goes fine until the time when their business got monthly check from their public cloud saying, well, this month you will pay $10 million again. And they realized that probably that's not too optimal, right? They performed such a great transformation, but they started to spend that extra money, or, well, somehow you can detect if you spend an extra money, right? If you can compare that to your previous spendings, maybe they spend less, but it is still a huge amount of resources, right? So all parties performed their work very well. Developers developed, cloud ops successfully deployed, DevOps prepared all the deployments. All went fine. What was wrong? How do we fix that situation? How would we behave to prevent it? Well, let's start from a far end. We prepare our applications, our microservices or monoliths, whatever. Nowadays, it's a typical approach to use containers to deploy them. To public clouds or some on-prem solutions, we package our applications. We tune that, we set and instruct some container management systems to actually run that containers. Well, and this is a long process, going from your source code to your production to your customers. And on that long route, we can sometimes lose very important information. about what resources are available, what are our requirements, also related not just to business logic and logical requirements, but also some functional requirements. Well, here what we must do. Of course, we must define the quality of service, saying, well, here are our promises, and here how we will measure certain metrics and see, well, our promises are implemented as expected or not. So it's a pretty straightforward approach that we can take here. We can define that SLAs. We can select some indicators, and that indicators probably should be related to our containers and our applications and runtimes that run our applications in that containers. And we must define certain criteria how to turn that indicators into a percentage or a binary answer about are our promises being met or not. Well, let's talk in some greater details about that objectives. What objectives can be? Different ones, but we prefer technical ones, of course. Not like we expect this button to be green. Well, yes, it should be covered by tests. But we want our system to be responsible. We want it to work fast. We want it to perform enough work to earn that money for the business. And that are really technical terms. And they are, of course, related to what happens in the JVM, especially to what happens with garbage collection, what happens with our compilation, are there any problems with errors. We can measure that, right? We can analyze that. We can collect some logs containing that indicators. And we must do that. I believe that this is the right approach to crack that problem. Well, we have two goals, and they may be in a conflict, right? Because we want to lower the usage of our resources. For example, memory. We can throw memory into application saying, well, that probably will help garbage collector, but that may become expensive. Or we want to reduce cloud builds. Let's cut our instances, the size of a pod, and try to survive and to tune all the parameters to meet all other expectations. So there's a bit of conflict here, but well, we can do both wrong. We can spend a lot of money and we still can miss our goals if we don't care about them. So think about how your production is underutilized. Think about what scaling strategy do you use. Think about how you choose and who chooses all the resource requirements, all the limits and requests for your particular application or for all the services that you have. Do you know the name of this person? Do you know the strategy being applied? Do you know that requirements? Otherwise, we will face this. From a formal perspective, nothing is wrong here. Every, what is that, carrot seed package is being sealed in a bigger standard container. And the company that ships that is the same company that sells you a public cloud. So they say, no problem. Just push your containers with high resource requirements and they will work. So seeds were delivered. But we know that we've spent a lot of resources here. In this particular example, we wasted some space, probably also time, right? Because someone could get their delivery afterwards because the transport was busy. So we should plan and we should optimize. And we try to optimize containers to make them more efficient, but what does it mean? In our containers, we are Java developers. In our containers, we run JVMs. And it wasn't forever that JVM worked fine in a container at all. So it could easily crash or make some damage to your system because it wasn't container aware. For a few years, it's not a problem. And people started to rely on that. Who really uses default JVM settings for their JVM in a container? Don't be shy. That's pretty normal. I only see a few hands here, but I don't believe you. Because the statistics from all the APMs says the reverse. Only few actually tune their JVMs in containers. And that's a common approach. Just, okay, default settings, they work. Okay, it's a black box, it's a container, we can run it. Well, why it is true? Because now JVM pretty much is capable of determine some safe settings and to run fine in your container. It's not an optimal performance, but at least it's safe. Well, remember that different tunings from outside of the JVM, from outside of your container, they influence what actually happens inside the JVM, what mode it chooses to run. Like it can select a compiler or especially a garbage collector based on the settings that you've put externally, like the size of the amount of memory available or the amount of CPU available to it. Well, we know how to determine the requirements for an application. If we know, we can run the application in different circumstances, try different settings, and to see what resources it actually consumes. How much do we need? In that case, we can say, all right, we will use certain JVM settings and certain settings for our containers. But how it happens, actually? Well, we nowadays most likely use Kubernetes. And this is a system that uses some description of how your deployment should look like after it's done or when it's reconciled. And it says, okay, if it's not so right now, I'll perform some actions for you. Like deploy a container, for example, on some node using a new pod and some container image. And we set some requirements for our Java containers. For that Kubernetes, write that YAML files. And what is especially important, we say what are CPU and memory requirements and what are requests and limits for that resources. So how much should we get as a minimum? What's the life requirement for the service? And what's the actual limit we shouldn't exceed? And if it's exceeded by somehow, and memory limit can be exceeded, then the application will be shut down, which isn't great, right? And what's good about Kubernetes and managed Kubernetes in different managed Kubernetes systems, that it automatically scales our production. It helps to survive some load, but when it scales, well, it sometimes scales unpredictably. An event like Black Friday happens, and we start to pay more and more to our cloud provider because autoscaler works, and, well, we have to do something. Well, how to save here? There are obvious strategies. For the services that are not that important, that are not critical, we can easily lower their requests, we can collocate them, we can just give them minimum, we can use spot instances that are cheap, that are well-known strategies. And it's not a problem generally. You should know what services are like that in first category. And critical services are much more tricky. We have to say, first of all, we don't have good vertical scaling in Java. So we have to set requests and limits probably equal to get optimal performance, optimal peak performance. And we have to select scaling strategy. Like how much do we pre-scale, or how much do we increase our capacity when the load grows? And what is the key metric we look at? So sometimes one of the most popular metrics is what? How do you think? The amount of CPU, right? And what does it say about the quality of your service? It says nothing. It just says, well, we burn that much CPU, probably we need to scale, but we don't have any good idea of what happens. So probably other metrics like the number of requests being processed or latency are more important. Sometimes it's impossible to scale if you don't break dependencies. If you depend on a slow database and multiple services go to the same database, they will be slow, we won't scale. So we have to resolve that or do the reverse if we have extra capacity in our dependencies. As I said, things, they still break, and we will see how scaling can be different or how it can be unobvious for a certain service. Let's look at the very well-known example. The version is not too much up to date, but it's about the same with the newer versions. So there are multiple ways how to containerize such a service. Probably you'll hear a dedicated talk next slot, but I'll just briefly mention some of them, like using Google Jeep or using plain handwritten Docker files or other means like build packs. What about some magic? Companies say, bring your applications to us, and they say, we have some tools. But there's no real magic here. Those tools help, for example, tools from cloud providers, help to prepare applications for their cloud. So you take the source code, and you get a container that works somehow, and you know that the JVM in the container also works somehow. Well, yeah, you have all the boilerplate inside. But what about the important part? Your Java options. There's no AI yet that says these are the appropriate Java options for this application. So many people said that they use AI results in their production for their code, but it would be interesting to hear whoever tried picking some Java options using the AI. Well, I don't know. And we can create a Docker file, and we can create it differently. For example, we can select one of the minimalistic images available to create a very slim container, which will make the deploy faster and is all the process of different deployments, etc. So instead of magic, there are great tools that can be used as standalone tools and also as a part of a more sophisticated Maven or Gradle build process, like build packs. You can use build packs to pack different kinds of Java applications, including Spring Boot applications, as a command line standalone tool. And you also can plug in them to your existing or new Maven projects or Gradle projects. In particular, for Spring Boot, it's very easy to create container images using Paketo build packs to switch between your classical JVM and native image variants of deployments. And inside you will get some layers with runtime, Liberica in particular, which is the default runtime. And you will have it all automatically for your CI or your developer build process, where you download all the tools under the hood, assemble everything that you need, assemble the container, so you only need running local Docker registry, and you publish that container, right? It's very easy. Well, and inside that container, you will have a very useful piece of functionality that looks at your environment when you start, also looks at some of options that you have provided, and picks the right JVM options for you. Here goes the magic. And this is, by the way, a magic written in Go, and some tooling in that source code for Paketo is written in Ruby, and all that is combined with Java, and it's so funny. We know how to determine certain requirements. Probably some of them will become unnecessary soon, like the number of Tomcat threads, right? Why? Because, yeah, virtual threads. Yes, we won't need real threads anymore that take 1 megabyte stack per thread. So, and if you have 200 threads, we will use 200 megabytes, which is significant. But still, we can manage that, and Java 17 is the default in Spring Boot for now. Anyway, we can build containers using Docker files and build packs, and we'll see intermediate build stack container images in our local registry, and we'll see the resulting ones. You see, using manual Docker files is somehow very promising. We can create very optimized, slim images, even more optimized than automated ones. But we also can use an automatically generated images that are also good. And they are updated, so you don't have to worry about many, many things. So what about the optimizations? Well, let's measure. Let's try to scale our instance built as a container and to see how putting that image and deploying it as a standalone application or in a Kubernetes actually works differently with different scaling settings. So we know the cloud where we are going to deploy. And that limits our choices because we can't afford some arbitrary machine. It will probably be a waste. It will be a waste. So we'll try different steps, different options. In this case, options available as for autoscaler. And we'll start with an application without any container. We'll see what happens there. So our SLO would be to keep the response latency below 100 milliseconds, which is reasonable, I think. And we'll look what happens with throughput of this application. So we'll try to harness it and to measure how many requests per second it is able to process while the latency is small enough. There's a warm-up process, so we will only look at the steady state, which is also important because the warm-up part is kind of tricky and there are multiple solutions to the warm-up problem. So for our example here, we'll look at the 100 percentile. And as I said, we'll start with a bare metal run. And we had, I remember this number, 1,100 requests per second for a classical JVM. And surprisingly, or not surprisingly, native image is much better here. So we see it 2,000 and almost 2,500 requests per second. So let's put this application into a container. No Kubernetes yet, just Docker. And, well, let's run it. So the number here is slightly lower, but still it's different. And then we'll start with a single node with a single pod. What happens then? Well, the performance dropped down dramatically. Who would notice that if that would be done by a different team? Saying, here's our nice service, here's the source code, please, ops team, deploy it. Ops team deploys it. And what happens? You get a bad performance. And they say, okay, well, we'll try to optimize it or maybe deploy more instances. But what would be the settings for the deployments? How we would try to determine the settings? So it all here happens within the same resource boundaries. So they take the same machine and we'll try to slice it differently into decent number of ports, and we will slice the CPU to see what's the optimal sizing for this application. So let's try the 4 ports, 4 smaller ones. will it be better or worse? No one knows. We have to try it. And here we finally restored our performance to the original one. Well, it's a bit strange, right? We went from original bare metal installation that we could also use in a public cloud, right, on the larger instance, to some setting for our managed Kubernetes. So let's double the number of pods here and reduce their size even more. And we see that we finally exceeded the original number of requests per second within the same latency boundary. And what's also important here, the original application has no obvious settings to behave better. So here we improved it by scaling, which is the goal. So here the Kubernetes helps us. We can improve it even more just by using more nodes. There are some important lifetime considerations, like what CPU is consumed during startup, because we here use much lower fraction of CPU, so the warm-up process will be much longer. But as I said, it's solved differently. But that's also an indicator we must look at. So what happens if we slice it into even less slices? Very, very tiny pieces. Well, it's generally not a good idea to give Java less than one CPU. And here we see it. It's still not that bad, so we have the advantage of many instances, but it is not as optimal as slightly larger instances that we've had before. And as stated here, all the improvements are non-linear, so we have to measure options. Well, what happens next? We can remember that we had that good performance with native image. Why won't we use that? And that gives a great profit. By using scaling in Kubernetes, we can increase the original throughput even more by using native images and many instances within the same resource budget. Great. We can scale such applications in Kubernetes, at least for this particular example. I will show you some slightly different demo in a hallway. Just catch me. And this is about memory. How memory consumption can be very different with very tiny changes in configuration of your application. So we know that scaling matters. That scaling can be done differently. So we have to measure, we have to perform testing, we have to select strategy for our deployment for SLAs, SLIs, and SLOs that we write for our program and that we actually track. We have to care about CPU and memory. These are very important resources because if we exceed the CPU quota, we are throttled. If we exceed memory quota, the pod is shut down, which isn't very good. It is possible to find memory requirements, but we have to run our program to do that. And typically, it's at least two-step approach. So we have some knowledge about the workloads that we must process, and we measure the actual memory consumption. What parts of memory, by using native memory tracking or other means, what's being consumed by our program. And we can also combine it with the knowledge or some facilities provided by starters or tools that look at the environment when the application is started and provide some good JVM settings. We can use different container images, but of course it's better to secure small or to use small and secure container images, and that really helps. And this is the way to build slim container images and to manage them smoothly in your production. And there's no alternative to some developer work or performance engineering work to tune your actual applications to scale them properly in Kubernetes. So, as I said, there are many tools to build container images, and the demo that is an extra demo is about build packs. So please, if you're excited about that, just try it. Please don't forget about your application testing. Don't forget about security updates and newer Java versions that are also related to security and performance. Thank you. These are my contacts. Maybe there are some questions if we have some time. Yeah? All right. Yeah, please.
The previous year there was also a presentation about the same thing, and that guy said to make bigger containers. So instead of having a lot of containers, have bigger containers and less containers. That is better. That contradicts a little bit.
But what? Okay, so the question is probably it's good to have bigger containers because I think that's because of reusing some components in the base layers. Actually, yes, but we can optimize the very base. Like last year, I had a talk about how much do we waste for the very base layer with your Linux and your JDK. So everything that's on top of that, your libraries, your Java libraries, of course, you can have an extra super fat layer that you will reuse. Especially if you have a technology for patching layers, so you could replace the down layer and have it all with very few updates. So yeah, I talk here about the base layer or base layers. Yeah, great question. Hey. Okay, if there are no more questions, please visit our booth that will open tomorrow, and I also will have a talk on Wednesday. So, thank you.